Having broken up the calc server into generic and specific modules and investigated some of the borderline cases which can occur when dealing with concurrency, you will probably figure out that there is no need to go through this process every time. In this section, we'll introduce a Gen Server OTP behavior module. It's a library module that contains all of the generic client-server functionality we've looked at so far. It gives us the ability to send synchronous and asynchronous requests, to start servers and terminate them. Generic servers are the most commonly used behavior pattern, and what they do is they'll set the foundation of all other behaviors. And just like in the examples we looked at so far, the green module here is the Gen Server module. It's part of the standard library application, whilst the red module is the callback module. It's a module you have to implement yourself, and obviously you can name it whatever you want. Now, if we're implementing an OTP behavior, the first thing we need to do is introduce a behavior directive in our module declaration. You can see the behavior directive at the top of the calc module. The behavior directive is used by the compiler to issue warnings over callback functions which might not have been exported or implemented. So as not all callbacks are mandatory, warnings are often ignored, and we'll see this when we now go in and compile it in a minute. And even more important than the compiler, however, is that the behavior directive is used by whoever is reading the code. It's usually the poor souls who have to support, maintain, and debug your code long after you've moved on to other projects. Generic servers and other OTP behaviors are started not with the spawn BIFs, as we've done up to date, but with dedicated functions which do a bit more behind the scenes than just spawn a process. With Gen servers, it's a start link function, which takes 4 arguments. The first argument will tell the server to register, will tell the Gen server module to register the process locally with the alias name. Now, it's an optional argument which can be omitted if you don't want to go in and register your server. Mod is the name of the callback module, and it's where all of the server-specific code you write yourself goes into, so where all of the callback modules can be found. Well, args is an Erlang term. It could be any valid Erlang term passed to the callback function, which will initialize your server state. Now, unlike the previous examples, args does not have to be a list. It could be a list, but it doesn't have to. And the fourth argument, which we will not look into in this set of classes, is a list of options, but it allows us to turn tracing on, spawn processes with a larger heap, and other features which have to do with optimizations. So start link gives us a synchronized startup. What happens is when we call start link, we first spawn a process, and this process will then go in and call the init module in the callback function, which we've provided in mod. The callback function will go in and initialize the state of the process and return a tuple of the format OK loop data. When the init function has returned tuple OK loop data, only then does start link return OK PID, where PID is the PID of the new server we've spawned. So it's a synchronized startup. It gives us more determinism when we're starting systems with many, many processes, as race conditions at startup might occur. And if certain processes execute before others, we might get crashes. So having a synchronized startup gives us determinism in that we'll be able to reproduce the fault from one trial run to another. So here is us starting our generic server in the calc module. We go in and we call the function start. We pass it the environment variable, and this results in the Gen server start link call being made, where we register the server locally with the name calc. The callback module is calc. The third argument is the environment variable, and the fourth is our list of options. This will spawn the process. It will then result in the init callback function being called, and as we've seen in the previous examples, the only thing we're doing in init is just giving some visual feedback that we're starting, that the server's been started, after which we return OK loop data, and in which our loop data in our case being the environment variable we've passed in. Notice one thing here, we're doing a Gen server start link, and we'll see why when we look at supervisors, whilst we're exporting the function start. We're doing that to retain the whole API from in this example flow, but if you were programming Erlang in a large-scale project, the start function would actually probably be called start link. So what happens if we want to do synchronous message passing? So we use the gen server call function. The gen server call function will send the synchronous message to the server, allowing the server to handle it in the handle call callback function. And it will wait for a reply to come in. So when the handle call callback function is called, it will go in, it will pattern match the message we've passed as a first argument. The second argument from will contain a unique reference and the PID of the client. Most cases we actually don't use it. The third argument to the handle call will be the loop data. So this is the same loop data which was returned from the init function. We handle that particular message in the handle call, and once we're done, we send back a tuple of the format reply with the reply we want to send back to the client and our new loop data. This gets sent back to the client, and the client process, upon receiving it, returns from the gen server call, returning the value reply. Now, this message exchange will follow a unique protocol, and it will contain a unique reference. It will match, which guarantees that the reply we actually get back matches the message itself. And what it also does, it will monitor the server, ensuring that if the server has crashed or crashes, that the call function itself terminates as well. So all of the borderline cases we've looked at, and many more we've not looked at, are handled for us in the gen server module, in the gen server behavior module. So let's implement the eval function in our generic server. And this is what it would look like. We export eval. Eval will take the expression, and this results in a gen server call. We do the call, we need to specify which server we want to send the request to. So in our case, it's calc. We send a message to the server of the format eval, expression. This is then handled in the callback function handle call. What you need to be aware of here is that we've placed our client functions and our callback functions in the same module. So our eval function right here is actually called by the client process, whilst the handle call function is called by the server process. So handle call will pattern match on the message, in our case eval expression. It will then send back a tuple of the format reply, the reply from evaluating the expression, and our new loop data. As our loop data is not changing right here, we just send back env without changing it at all. Now, this is synchronous message passing, but what happens if a client needs to send an asynchronous message? If the client needs to send a message to the server but does not expect a reply, it does so using the gen server cast function. The gen server cast function will take a message, and it will forward the message to the server. As soon as the message is sent, the gen server cast function returns the atom OK, and the server then receives the message in a callback function called handle cast. And handle cast will pattern match on the message in the first argument. The second argument is the loop data. It handles that message and then sends back a tuple of the format no reply, new loop data. So what we're going to do now is we're going to implement an asynchronous print function. We've not done that before, but just to show you what if we want to go in and print an expression. You might remember from Simon's example, expression print will take an expression and convert it to a string. So what we do is if we want to go in and print an expression, we call the client function print expression. That will do a gen server cast to the server. That's handled in the handle cast function where we pattern match on the message in the first argument. We call expression print with the expression itself and get back a string. We do an IO format on that string and then just return back our no reply, loop data. And we'll bring this on a trial run in a minute. But before we do that, what if we want to stop generic servers? So far, we've seen callback functions in it, handle call, handle cast. Now, all return OK loop data, or reply loop data, and no reply loop data respective. If we let handle cast return stop reason loop data, this will cause the server to terminate. Now, the gen server module will receive the keyword stop, and it will treat it specially. And what happens is that the terminate callback function will be called. Terminate takes two arguments. One is the reason for termination and our state. And it allows the server to clean up after itself. And once it's cleaned up, the server itself terminates it. Terminate can return any value, and that value is just ignored. So, looking at our calc example, what we do is we stop our gen server by calling the stop function. The stop function will send an asynchronous stop message to the server. Now, the stop message could be any message. The stop in the stop client function has no meaning. The meaning it has is the meaning the handle cast function, callback function, gives it when it pattern matches and returns back the stop atom in the tuple stop normal environment. Note here, the reason for stopping, which is the second argument to stop, is set to normal. Anything other than normal will actually cause a crash report to be logged, or an abnormal termination report to be logged. So usually if we're shutting down behaviors gracefully, the reason for stopping them down will be normal. Having sent stop back to the gen server module, it will call the terminate callback function. Terminate will take two arguments. One is the reason for termination, and the other is the loop data. In our case, all we've done is just print terminating just to get some visual feedback. Although servers can be stopped normally by returning a stop tuple, there might be cases where they terminate as a result of a runtime error. Bugs happen, corrupt data happens. And if this happens, the generic server, and the generic server is trapping exits by calling process flag trap exit trueBIF, terminate will also be called. Now, if you're not trapping exits and the process terminates abnormally, terminate will not be called. Now, if we are trapping exit and terminate is called, the reason will be the reason for termination. It could be a bad arg, it could be a bad arif message, or inexistent function call, or any other of the runtime errors which occur. Let's just take this gen server for a trial run and see what happens. Okay, so we've got our gen server module here in the left frame. We'll go in. We compile it. I've already compiled expression. We get our environment variables. We do a calc start, which this is the function which goes in and calls gen server start link. And we get starting printing. It's process 45. We do calc eval. So we need to first bind expression. We do calc eval of the expression, and this will send the request to the server and get back -1 as an answer. If we now do calc :print with the expression, what happens here is the gen server prints the expression, whilst calc print returns the atom OK. The atom OK is the return value of the gen server call. And let's try stopping it, see if that works. Yep, system working, seems to be. So in this section, we've covered gen servers. Gen servers are a great improvement over a situation where every company, project, and potentially developer goes in and reinvents their buggy client-server implementations. Other OTP behaviors which we've not covered include finite state machines, event handlers, and you're in fact also given the framework to write your own. We call them special processes. Now in the next section, we will look at another behavior called the supervisor behavior.